Okay, so let's talk about the area between curves. So in this case, let's just start off with f and g. So usually what we remember is the area underneath the curve of f is just this total region over here. Now, if I'm looking for the region between, it's going to be the area of the total area minus the area of g. In that case, the total area minus the small area, you get the chunk in the middle. So the area of the between curves in this case would be just f minus g. So in that case, f is this total area minus g, which is this area over here. So the difference between these two is just going to be the area between. Now, if we write that as an integral, you have to remember that the bounds of your x's are not from a to b. Okay, so in that case, from a to b of f of x minus g of x gives me the region between the two curves. Now, if I have another question, this is another example, say if I need to integrate this function with respect to x. Okay, so you're bounded by y equals square root of x, y equals x minus 2, and then y equals 0. Okay, so step number 1, you need to go ahead and draw the graph. Okay, so let's do this. So my graph looks like this, square root of x looks like this, y equals square root of x, and then y equals x minus 2, which is here, y is equal to x minus 2, and I'm bounded like this part over here. So in that case, y is equal to 0. In that case, that's my x-axis, this is my y-axis. Now, as I mentioned over here, it's always the top function, f, minus the bottom function, g. Okay? So looking at this example, if we are integrating with respect to x, think about my partitions. In that case, my partitions is going to be vertical because I'm changing with respect to my x's. Okay? So in this case, I am bounded by this function, and this function. So the region of interest is just going to be this region over here. So let's go ahead and just draw vertical lines because that's my partition it's going to look like. Now, as you may have already noticed, it's not bounded by the same function. So in this region let's draw a line here. From A to B, there's a point C where the top is bounded by the square root of x and the bottom function is bounded by y equals 0. Okay? And then the other one is you're bounded by the top, which is over here, by square root of x, and the bottom is x minus 2. Okay, so based on this situation, you have to break this up into two separate integrals. Okay? But before we do that, we probably need to go ahead and find the points of intersection. Okay, let's go ahead and write the points of intersection. Okay, well, first of all, for this point C, it's going to be at x, that's when y equals 0, so that means this C is equal to 2, and this part here is going to be 0, and we need to look for what is B. So when you look for B, it's going to be the intersection between these two curves. In that case, x minus 2 is equal to square root of x. So let's go ahead and solve this. So in this case, solve for this, in that case, get rid of the square root. In that case, x squared minus 4x plus 4 is equal to x. We're left with x squared minus 5x plus 4 is equal to 0. And you get x minus 5, x minus 4, x minus 1 is equal to 0, so x equals 4, x equals 1. Okay, the reason why I have x squared here is I squared both sides. Okay, hopefully you get that. Now, you end up with 2 points over here. You might be wondering, which one do I pick? Okay, so when you square this function now, this is going to be x. In that case, x, and then this one x squared. So in that case, it's going to be this part over here. In that case, the other part is this point over here, but we're only looking at the positive component of my y. Okay, so this is the one we're going to look for. Y equals 4. Because x equals 1, this is this point if you connect this point at the bottom. Okay, because when you rewrite that, you square both sides, and this is going to be y squared equals x. So in that case, you have this bottom part. But you're looking at this positive where y is greater than 0. And x is greater than, well, y is greater than 0. So that is my point of intersection. So that means B is equal to 4. Okay? So, like I mentioned, we have to look for the area between the two curves. In this case, this is one curve, this is a bottom curve. So in that case, let's call this region 1 and this region 2. Okay, now remember, the area is equal to the integral from a to b of f minus g dx. Okay, So I like to call my f as the function on top, and g is my function at the bottom. Okay, so in this case, region 1, I have this region 1. So in that case, the top is bounded by square root of x minus the bottom function, which is 0, dx. I'm integrating between 0 and 2. Okay, so that's region number 1. Okay, you have to go ahead and integrate that, which is pretty simple, but because of time constraints, we're not going to do that here. Okay, now region 2 is this region over here. So which one's function on top? Okay, it's still this one, right? So it's going to be square root of x minus the bottom function at the bottom. In that case, it's going to be x minus 2. So make sure you put brackets in there. X minus 2 dx. Integral, sign, and then what are my bounds? We're going from 2 all the way to 4. Okay, so in that case, that would be my region, area of region 2. So the area of this question is going to be region 1 plus region 2, which is equal to, in summary, from 0 to 2, square root of x dx, plus integral from 2 to 4 of square root of x minus 2 dx. Okay, again, you have to go ahead and integrate that, and you'll get the answer that you need. Okay, now, if I were to do this question again, but I'm integrating with respect to y, okay, that means you probably have to turn your head 90 degrees to determine which way is up. Okay, so in this question, example number 2, we have to integrate it with respect to y. So that means all your variables now need to be written in terms of y. So that means over here, x is equal to y squared, and over here, x is equal to y plus 2, and y equals 0 is still what it is. Okay, you can't do much about that. Okay, so let's go ahead and draw this diagram. Okay, of course, it's going to look exactly the same as this. So let's go ahead and just draw this. So in this case, we have that. But because of this question, we are restricted by boundaries where, in this case, y is greater than or equal to 0. And again, y is greater than or equal to 0. Again, that's just the first one is important enough. Okay, so let's go ahead and draw this. Okay, the top function here, let's rewrite this. This is x is equal to y squared. And this one is x is equal to y plus 2. Now, how do you determine this is which function is on top? So what I'm going to suggest you guys is turn your head 90 degrees to the right, look this way, and this is always going to be the one on top. Okay? The one thing about this is x is going positive. So x is taller, just think of it as becomes my y. So in that case, this is my function, and that's what I get. Okay? So now, because we're integrating with respect to y, I'm not going to pick values over here now. I'm going to pick values over here. Okay? So the reason why I pick over here, because we're integrating, my partitions now are going to be horizontal. Okay? Well, always remember to label your graph. This is my y, this is my x. Okay? Because I'm going to start from 0 and move away up. Okay? This is up for y, so in that case you're going to start from here and move the way up over here. Now, because from this question, we know what this point is in terms of x. Okay, so this point of x, we even know this part here is equal to 4. So plug this in. Y is equal to, either one will do, 4. So 4 plus 4 is equal to y plus 2. That means this point here is equal to 2. So we integrate from 0 all the way to 2. Okay, just remember that. Now, sometimes you might be wondering, like, which side do I pick? Okay, okay, let me just go and do this first. Okay, so in that case, the area is bounded by this one, and this one. So as we said, turn your head 90 degrees to the right, determine which function is on top. So in this case, the area in this case is, this is the function on top, so in the case is y plus 2. Subtract the bottom function, in this case y squared dy, and look at my bounds. I'm looking from this way to 2, so I'm going from the bottom to the top, so 0 to 2. Okay, again, whatever answer you get, it's going to be units squared. Okay, again, it's whatever this thing, unit squared. Okay, because the reason is area is 2-dimensional. Okay, so just make sure you have units squared. Okay, so you might be wondering, like, sometimes which one to pick. Do I integrate with respect to x or in respect to y? Does it matter? The answer is, to some extent, yeah, but the area will yield the same thing. Okay, so that, just remember, if you integrate with respect to x or y, you get the same answer. Okay, so to answer the question, which do you pick? Well, number one, if the question is, if you can't pick because the question says integrate with respect to x, and the other one is with respect to y. In that case, you can't pick. Well, the other one here is if you have functions that you have to integrate by hand, sometimes one is easier than the other. So for example, if I have y is equal to tan of x, or x is equal to arctan of y. What do you think is easier to integrate? This one, we can rewrite this as sine over cosine and use u sub, but this one, you have to use your calculator. So hopefully this illustrates some of the reasons why one is easier than the other. Okay? Now, the other way to determine which side to integrate is whichever is easier to integrate. For this one, we have to integrate between two regions. Break this up. You have to write two integrals. Whereas this one, you just have to write one integral and you get the job done. Okay? So either way is fine. So whatever the function is, pick the one that's easier to integrate. Okay? The less algebra you have to do, the better it is. Because the most common mistake in calculus is always algebra. Okay. So now, last example, example number 3. Okay. This one is where it changes which functions on top and to the bottom it changes. So this is y, this is f. Oh, sorry, this is f and this is y. So this is, let's call this region 1, R1, and this is R2. Okay, so let's just go ahead and just integrate this, set this up. Okay, now you might be wondering which one do I pick? Do I pick x or y? Okay, so if you turn your head 90 degrees, if you draw vertical lines over here, okay, this is bounded by this function and this function, this function and this function, so you can't do much to rewrite. So because of the restrictions like what I mentioned, you can't integrate in that manner. Okay, so in that case, it'd be easier if you integrate from in terms of x. Okay, so if you draw this up, you end up with this. Okay, as always, just set it up. So my area is equal to, in this case, it changes, right? So in this case, for this region R1, this is the top function. And this top function is f and the bottom function is g. Whereas our region 2, this is g on top and f at the bottom. So in that case, you have to pick one or the other. So in this case, area is equal to region 1 plus, okay, let's just rewrite this. Area is equal to region 1 plus region 2. So R1 in this case is between A to B, which one's function on top? My function on top is f minus my function at the bottom, in the case g dx. Okay, region 2 is equal to integral between B to C, and then you have the bottom top function is g, bottom function is f dx. That means my area is equal to the integral from A to B of f minus g dx, that's region 1, plus from B to C of g minus f dx. Okay? In that case, that is in cases where the function changes, like on top and other. So then this example is if the function intersects more than one point. Okay? So that's what it is. Okay? Hopefully that makes sense. I'll see you in the next video.